Hey folks, this is our seventh episode. I'm going to cover the things you need to do assignment 7. The let's just jump right into it. The point of this assignment is to let us figure out strategies for dealing with exponential equations like this kind, y equals a times b to the x. So notice that there's 4 letters, right? So there's a lot of variables. In the text, they are making a funny distinction, and I think they're using the language poorly. So I want to give you better words to use to think about this stuff. Usually, you think of there's a distinction between what are known as constants and what are variables. In a typical problem, the a and the b are fixed numbers, right? So while you're using a letter for them, we're only using letters in an order that we may be thinking kind of generically. But x and y, those are actually allowed to slide around, to change during a particular problem. So that's the distinction. X and y would be called variables. A and b are constants. Now, that's just typically the case. There are scenarios where you might think of this differently, but that's the usual setup. The point really is if you've got 3 out of those 4 that are known, then you're going to be able to solve. You can figure out the 4th one if you know any 3. So I do like to use this terminology. I think it's more useful. Talk about knowns and unknowns versus what's the variable. Because everything is a variable. But I mean, it's really just a linguistic distinction to say that some things are constants. Everything where you're using a letter in place of things that usually would be numbers, that's a variable. All right, so here are the 4 cases that I would distinguish. Let's just go through them one at a time. Y could be the unknown. Now that's the thing on the left-hand side of our equation. Y. Hey, I wonder if it would be useful for me to write the y equals a times b to the x on this sheet that I'm using to cover up the junk before we get to it. Yeah, so y is the unknown. Well, if that's the case, you know what a is, you know what b is, you know what x is. Raise b to the x power, multiply by a, boom, you've got y. That is, you just plug in. That's the thing we called a direct problem before. What if x is the unknown? You know what y is, you know what a is, you know what b is, but x is left as a letter. That's an inverse problem, and we'll solve that. It's actually really easy because we have the inverse functions now, the logarithms. So we'll use logs to solve such problems. The other things, a, for instance, could be the unknown. Now, that sounds bizarre if you think about it, because a is the amount you start with, the amount at time equals 0 or x equals 0 in one of these problems. In what scenario would you not know how much you start out with? Well, there are examples of that. It's not that you don't know, but you're trying to decide how much to start out with. Anyway, well, that's an easily handled case. And the last one, where b is the unknown, this is a little tougher, but you're going to end up using roots. And I don't mean like square roots, but generic roots, roots to whatever power. Okay, so I've got numbers 1, 2, 3, and 4 on there. Let me pop up a browser and show you how this looks in the book. Oops, I got the wrong screen on the browser. There we go. So this is the strategies, they call them, that they have in the book. And you'll notice that strategy A corresponds to my case 1. That's where everything is known except for the thing on the left-hand side of the equation, the value. But the thing I identified as 2 is actually C, and B and D are the other ones. Okay, so we're going to go through each of those types, but I want to go through it in sort of my notation rather than theirs. But just so you have a way to translate, let's make that explicit right here. Y is the unknown. That's the same thing as their strategy A. X is the unknown. That's their C. If A is the unknown, I hope I've got this right. That's their B. And then last one where B is the unknown is their D. Yeah, that's correct. Okay, so I guess the best way to do this is to just give examples. So that's what I'm going to do. So the first case where we know everything except the amount at some future value. So we'll know the interest rate, say, if we think about it as a money deal, think of it as interest rate. You might know the initial amount, and you might know how much time has elapsed. So here's an example of strategy A, type 1. How much is in an account sorry, I just realized that I could use the pause button on my recordings and not force you to sit through watching me write out something. So here's the question. How much is in an account bearing 4%? This is continuously compounded interest. If 5 grand was deposited 3 years ago. So that's a key word, by the way, that tells you that the formula you should use is PERT, P-E-R-T. But we should think of that e to the r as being b, and I guess t is really x. So, and p, what's p? P is a. Right? These are just, letters. They're different letters for the same ideas. The initial amount is $5,000. The base of the exponential is e to the r. So we're going to need to know what is e to the 0.04. I'll work that out in a second, but for right now I'm just going to write e to the 0.04. And then how much time has elapsed? That's the x. That's 3. So back to this screen, we'll pull up a GeoGebra, and I have it already opened. We'll just want to know what is e to the 0.04. Why is it not? Got to click in the window. Excuse me. Okay, so that's interesting. That number is really close to just being 1 plus the interest rate, 1.04. It's just got a few. Excuse me, there again. It's just got a few more digits down the line a little bit, but all right, what we've got then, oh, I got to transition back, sorry. What we've got then is 5,000 times 1.0408. Yeah, that's enough. I don't need that many decimal places of it, to the third power. So we can get a number. Oh gosh, now I got to go back to GeoGebra and actually get us that number. What is it? Well, actually, you know what? We can probably just edit the thing I just did, because after all, that e to the 0.04, that's our b. I'm going to see if I can put parentheses around that. Yay. And we'll be raising that to the third power, because that's how much time has gone by. And that whole thing needs to be multiplied by $5,000. All right, 56, 37, and 48 cents. So that's pretty good. I mean, it's not a great amount of money, but you've earned $600 of interest on a $5,000 investment in a few years. Yeah. So that's a type 1 or strategy A example. What should a type 2 example look like, or what they call strategy C? Well, that's where you're going to know how much you start with and how much you want to end with, but you don't know how long that's going to take. So that's what you're figuring out. How long does it take? All right, so I wrote out the example while the recording was paused. I'm kind of proud of myself, saving some time. Uh, well, but we've got to read it. So this is the type 2 or strategy C type question. I decided to put it in a sort of a finance setting. Suppose you're working for a corporation that's got valuable assets, perhaps a machine or something that is being used in production. These things can be quite expensive, and so you originally have a $3.8 million thing. Companies depreciate those things because there are tax advantages to acknowledging the fact that it becomes less valuable over time. It's being used up in a sense. So when this is just a made-up example, but suppose we're depreciating at a 12% annual rate, and then you want to know, well, when does its value get down to just be $2 million? What is known and what is unknown here? Well, the question asks you to figure out what time it is. When will it be that its value is $2 million? So that's the x. That's the value that's in the exponent. That's why this is a type 2 or a strategy C problem. What do we know? Well, we know the initial amount. That's A is 3.8. I'm just going to use the units of millions of dollars, so we don't have to have a whole bunch of zeros after every number. The base is known. It's a little bit tricky to figure out, but see, they're telling us that it's depreciating, which means going down at a 12% rate. That means 0.12, actually negative 0.12 is the rate. So B is really 1 minus 0.12, which is, can I get that as a decimal in my brain? 0.88. What else is known? A and B. X is not known. Oh, we know what y is. We know what the output of the exponential expression is going to be. It's this 2. So just take all that junk and write it down into an equation. We'll then solve that equation. Yeah, so 2 is 3.8 times 0.88 to the x. So we know everything except for x. How are we going to work this out? My advice is first just do division. Right, get rid of the 3.8 that's on the right by dividing both sides by it. So we'll have 2 divided by 3.8 on the left, and we'll have this 0.88 to the x on the right. It might help us to actually get a number for that. And, I'm not going to pop open GeoGebra. I'll just use my calculator here for a second to get that number. 2 divided by 3.8 is 0.5263. I'm going to keep that many decimal places on it. 0.5263 equals 0.88 raised to the x power. So this is a really typical situation. Actually, I feel guilty. I should have written that on a new page. So let's do that now. 0.5263 equals 0.88 raised to the x. Anyway, here's where logs come in. If you have a variable in the exponent, if you apply the logs to it, that rule about the how logs of exponential expressions works out, it pops the variable out of the exponent, and then you can work with it. So I'm going to use my favorite log. I like the natural log. You may prefer the common log, or if you want to do log base 2 or something strange, go ahead. But I'm just going to use the natural log on both sides of this equation. And first I'm just going to write it down as if I just took the natural log of both sides. But I'm going to almost immediately work out what that thing on the right side is, because remember that x you can think of it as just popping out of the log. So we get x times the ln of 0.88. 0.88 stays in the log, and on the left-hand side we still have the ln of 0.5263. Well, that may look horrible to you, and at first I'm sure it does, but one thing you need to recognize is that when you have the ln of something that's just a number, well, that's something that also is just a number. So while this thing looks complicated, it's just some number. We could get a decimal value for it really quick. I almost don't want to, because in the end, what I care about is what x is. So I'm going to say, solve this whole thing for x. What you would do to do that is divide by that number, divide by the ln of 0.88. So at a high level, at the 1,000-yard view of this thing, you just have a number equals x times another number, okay? Just divide by that second number and you'll get x. So x is the natural log of 0.5263 divided by the natural log of 0.88. So now I guess we better get into GeoGebra and get a numerical value for that. What am I doing? So what's that? Oh, gosh, I gotta learn to type again. Okay. I hope it understands it if I just type ln. I might have to pull up the keyboard and put the logarithm from there. 5263, oops, 3 divided by ln. Oh, it is understanding me just typing ln. Cool. And what did it give us as a number? 5.02. So that's pretty cool. We've got a nice value for this quickly. Again, I'm just going to write it as an approximate value because we don't need to carry all those decimals along with us. You might think about what units would this be in? You probably should always ask that question. What units are we talking about? But this was the problem talked about annual depreciation, and so that means x is measured in years. Okay? And so we've got 5 and a few days, 5 years and a couple of days, because 0.02 isn't really much time on the scale of years. I guess I could figure out exactly how many days it is, but honestly, if your boss is asking you this question, tell him 5 years, not 5.02. He doesn't care about the 0.02. He cares about roughly how many years. All right, let's get an example of my type 3, which is their strategy B. Right, so this is an example where this scenario where you don't know the initial amount would come up. You're asking a question about the future value. You know what you want to achieve at some point in the future, but you need to know, well, how much am I going to need to put up right now in order to make that happen? So let's read the question. How much money should be invested today in order to get $100,000 in 20 years' time? And let's assume 15% is your annual growth rate. So I'm thinking about like stocks, for instance. If you're playing a market fund, it's typical that you've got about a 15% growth rate over time. Okay, so here's an example of a type 3 problem, or what they would call strategy B, which is the scenario where you don't know the initial amount. But you do have enough information to figure out the other things. Okay, so it's asking us how much money should be invested today in order to get $100,000 in 20 years' time. That's a future value of money kind of thing. You want the future value to be $100,000. It's even given us an assumed growth rate, 15% annual. It's a little bit high, but actually just in stock index funds can achieve something close to that level of growth over, well, historically, not so much for this year, but generally the markets are going up in the 10 to 15% range. So, all right, we do know how much we want to see in the future, or when t is equal to x, t is equal to, what the heck is the time? Oh, here it is, 20 years time. So that's our x. This $100,000 is our y. The 15% tells us our rate. It's really b is going to be 1 plus 0.15 or 1.15. Yeah, I think I can write down the equation involving all these things. We have 100,000 is the output, or on the left-hand side. The unknown is the a, right? And then we do have the rate, or the growth constant, growth factor, 1.15. And we do have the time, or the 20 years that have elapsed, the x. Can we work out what a is from that? Yeah, see, a is just multiplied by this number, 1.15 to the 20 is something you can evaluate, and it's a number. All right, so maybe we should do that. But let me write it first as just saying, look, a is going to be 100,000 divided by that 1.15 to the 20th power. It would look better if I put parens around that thing. All right, so switch over to GeoGebra and see what that number is. I think I can just go ahead and put it in directly. So 100,000, that many zeros, divided by 1.15 raised to the 20th power. $6,110. I don't know about you, but I was surprised by that when I heard it. You only have to invest $6,000 today to get $100,000 in 20 years' time? Interesting. What's the number again? 6110. That is actually intended to be an object lesson to people of roughly your age. If you put a little bit of money away today and don't touch it for nice long stretches of time, like 20 years, it'll grow and it'll be significant, right? $100,000. Well, you know, if you've got maybe a 40-year, 45-year working professional life, think about what that $6,000 would grow to in 45 years instead of 20 years. It'd be in the millions. So yeah, doing some savings now can really help you in the future. All right, so let's see. Last example of one of these scenarios. Here's where we don't know what the rate is. We don't know what the base of the exponential is, but we do have other information that tells us everything else. In this case, I'm giving you one where we don't actually know what a is either, but we can sort of work with that anyway. Doubling time is a concept that's really a good way to sort of compare different things. How long does it take an investment to double? So that depends, of course, on how the interest rate is growing. In this one, it says to assume annual compounding. So the formula there is y equals the initial amount times 1 plus the rate raised to the x power. X is the number of years, a is the initial amount. Which things do we know? Well, we actually don't know a, but since it's a doubling time thing, I know that what I want for the output is twice a. And then it's real quick to just divide both sides by 2. Excuse me, divide both sides by a. I'm doing a recording. 2 is 1 plus the rate raised to the x power. Actually, we know what x is too. X is 12. Right? That's the 12 years that are in the problem. So what we need to figure out is 1 plus r. All right. 2 is this unknown thing. Let's call it b for now, raised to the 12th power. So basically what this says is I know the 12th power of b. How can I find what b is? You need to take the 12th root. So in practice, b is the 12th root of 2. I say in theory, I should have probably said that, but the practical way to do this is if you have b to a power, rather than thinking about roots, write the 1 over that power. That is, you could think of this as b is 2 raised to the 1/12th power. And that's something you can do in GeoGebra. Or I think you can take 12th roots in GeoGebra too, but it's often quicker to put in a fractional exponent, which does the same thing as a root does. I hope everybody knows this. Like 1/2 is the same as square root, 1/3 is cube root, at 1/12th is 12th root. And what number does that get us for b? Let's transition to GeoGebra and find out what it says. 2 to the 1 divided by 12. It says it's a 1.059. All right, so I'll swing back to the video camera view. Remember, that's really 1 plus r. So the rate you're interested in this one, well, approximately anyway, is the 0.059, or 5.9%. I'm off the screen, aren't I? 5.9%. Which isn't bad. It's roughly a 6% interest rate will get you a 12-year doubling time. Cool. All right, so that's the 4 that are identified in the book. I wanted to actually give you guys one sort of extra scenario. This actually happens relatively frequently. You can have multiple unknowns if you also know sort of multiple instances of the knowns. So here's an example of that kind of scenario. You've got an exponential function, or rather you're asked to find an exponential function that goes through 2 different points. Now what that is 2 different xy pairs. So I can write down 2 equations here. The assumption, though, is that it's an exponential, so y equals a times b to the x, right? But this goes into 2 bits. One that says, let's see, the first one is 24 equals a times b to the 1. And the other one is 3 is a times b to the 4. Now, this is this ought to feel a little familiar to you if you think back to finding the equation of lines that go through 2 points. It's really a similar process. You look at this at first and you go, I have no idea what I could do. But after a bit of thinking, notice something. If you divided one of these by the other, one equation by the other, the a's would cancel. So let's just see what that would look like. If I had 24 over 3 on the left, I would have a times b on the right, and with a times b to the 4th in the bottom. Okay, the left-hand side is just 8. The right-hand side, see how the a's cancel? And we've got b over b to the 4th. When that's really b to the 1 over b to the 4th. And when you have a quotient involving powers, you just subtract. So this is b to the negative 3. So can we figure out what b is if we know that b to the negative 3 is 8? Yeah, it would be 8 to the negative 1/3, which is, I'll just give it to you, that's a half. You can put that in a calculator and see. Interesting. Now, we know what b is, and we still have these pieces of information about the values of the function at different x values. With b known, the b's there are 1/2. Pick one of these, it doesn't matter which, but pick one of them and use it to solve for a. Because in that, now that we only have a single unknown in what is really just an equation involving multiplication. Since we get to choose, I'm going to choose that one rather than that one because I don't want to take the 4th power. Right? And it's fine. We can do that. So here's the equation that comes from plugging back in our value of b into the first of those 2 equations. You get 24 is a times 1/2 to the 1 power, which is just 1/2. And that means A is 48. A is twice. You have to multiply both sides by 2 in order to get that out. So A equals 48. Cool. Well, that means we've got the equation. Let me just somewhere write it as a sort of final answer. Y is initial amount of 48 and a growth factor of 1/2. Oh, so it's actually not a growth factor, but rather a decay factor to the x. Let me just, one quick last thing, we'll transition back to GeoGebra and verify that we did that all right. So I'm hoping to see the points, what were they again? 1, 24. That's 1 point. And the other point was, where was it? 4, 3. Now that one's visible, but the other one is not so much. The problem is we gotta zoom out to see it. How much do I have to zoom out to see it? There it is finally. Cool. And then the exponential decay function that we produced was y equals 48 times, that's right, I'm just going to go with a decimal, 0.5 raised to the x power. Well, look at that. That exponential decay function goes right through the 2 points that we wanted it to go through. So we did our job right. Okay, that's it for today. Hope you have a great rest of your day, and I'll be back with another one of these videos shortly.